Hi everybody, I'm Kajari, and I'm the pumpkin on the corner. And I'm going to be doing tries today, and Jaren is going to be doing graphs. And
Hi everyone.
okay, so um,
And I'm going to be running the slides, so you guys just tell me when to change next. My name's Amy. Hi, everyone. I have a sore throat. Sorry. All right.
okay, so if you go to the next slide. Okay, so we're going to be talking about tries. Going to say what they are, what they're used for, how to implement one, and I forgot a fourth bullet point here that says how to use them. So we'll go through some questions that you might get asked in an interview, or like you should just know how to use them. And we'll go through some of those questions. And then, Jaren, if you wanted to say what we were doing with graphs.
Sure, sorry, I had to unmute myself. So if for those of you who were here for the last session where we went over trees, we're going to go over a related data structure called graphs. Trees are sort of a special case of graphs. So we're going to go over what graphs are, what types of graphs there are, so just like a general case and then getting a little bit more specific. And then traversal algorithms, DFS and BFS, or depth first search and breadth first search. All right, back over to you, Kajari.
Okay, cool. Thank you. Okay, so if we go to the next slide. So to start off with, I got all of my source material from this YouTube link over here, and you should really go and check it out because it's a really good link. It really goes in depth, and like all the material that I have on this slide is from there, just in a shorter format. Okay, so next slide, please. Okay, so what's a trie? A trie is basically a tree. It's a tree that's used to index words or suffixes, or it's a good way to index text, basically. It comes from the word retrieval, and it's those 4 letters in there, trie. And you can use prefixes or suffixes, so you can use it, you can index it using starting from the start of the word or from the end of the word. Okay, next slide, please. Okay, so yeah, here's just another representation of it, and if you that's the string that we have over there, the ABAABA, and the trie on the right is a suffix trie of that string. Okay, next slide, please. Okay, and we have on the right, we have a suffix tree of banana, and on the left, we have a prefix tree of the words that you see below there, to, tea, ted, ten, and so on. And this is just a quick, like, this is what they look like. Don't worry if you don't understand them. We're going to go into building them later. Okay, next slide, please. All right, so tries are really useful when we're working with text. So think strings, think substrings, think lots of text. So some of the applications are predictive text or autocomplete when you're typing in a website, and you have those like libraries that do autocompletion or auto-suggesting for you. They probably use tries. Or for full text searches. So when you hit Control and F in like your PDF and you want to look for a word, you can use tries to accomplish full text search as well. Okay, next slide, please. Okay, so on the left again we have the suffix trie of the ABAABA string. You can also have it as a prefix trie, and on the right you have a compact trie, and these are actually called trees. So you call them suffix trees or prefix trees, and these have better runtime operations, but we're not actually going to go into them today and we're only going to do the tries because tries are a simpler data structure, even though they're more inefficient, but understanding tries, which are on the left, will help you understand suffix and prefix trees, which are on the right. So we're starting at the beginning, which is the basic but dumb structure trie on the left. Okay, so Next slide, please. Okay, so suppose you're given a string, A, B, A, A, B, A. To construct a trie, the first step that you do is you add a special character to the end that will just help you know when the end of the suffix has been reached. So you add your $ to the end, so your string T becomes ABAABA $, and then you write out all the suffixes, which we've done on the right. So up there, that's the string, and then right below it we have the numbers, and that's just denoting the distance from the first letter. So, you know, A is the first letter, so it's 0 from the first letter, B is the second letter, and so on and so forth, right? Okay, and then right below it we have all of the suffixes that we can make of this word. So the first one you'll notice is the string in its entirety. The second one is just the whole word minus the first letter. The second one is the whole word minus the first two. And you basically do this until you get to the whole string minus n letters. And you'll notice the last suffix of this tree is actually the empty string. And that's why we have the $, because it helps us keep track of the empty string and then like where the suffixes end. Okay, so you write out all the suffixes with the $, and then if you go to the next slide, please. Yeah. Okay, so you start with the suffixes, and you make a root node. So Amy, the next step will have a bunch of animations, so I'll just be telling you to click when I want you to get the tree to animate and bring out the next step. Okay?
Sounds good.
Cool, thanks. Okay, so if you click, we'll get the root node, right? So this is your root, this is where you start. And you start with the first suffix on the left, so that's the whole string. And from the root node, you look if you have any, you look at the first character of your substring, which is A. And from the root node, you see if you have an outgoing edge to the node A. And right now, obviously, since you're just starting out, you have no outgoing nodes. So you create the outgoing node A. So if you click, you get the node A. So then you look at the second character of the substring, which is it's still the first substring, right? So look at the second character, and now you're at this this A node, and you look for an outgoing node to B, which is the second character, and it's not there, so you create it. Now you look for an outgoing, now you look at the next character, which is A. You look for the outgoing node. There's no A, so then you create it. So click, please. Then you get an A. So you do this until you just complete the whole string. So you look at the next character. It's an A. You don't have it. You create it. B, you don't have it. Create it. A, you don't have it. You create it. $, you don't have it. You create it. Perfect. Okay, so now we're going to do the next suffix, which is BAABA, $. So you start at the root node. You look if you have an outgoing node B, and you don't. So you create it. And you do this for the rest of the substring. Okay, so now we're, sorry, not substring, but suffix. Now we're on the third suffix, which is AABA. So we're at the root node, and we look if we have a character A. And we do have a character A. So we travel down it to that A node. Then we look at the next character, which is an A. And you realize that from that node, you don't have an outgoing edge A. So now you create that outgoing node A. If you please click. And then you create all of the other ones too, because as they're new nodes, you don't have them, you create them up until you do that. Up until you have the new branch, Ches. Okay, so now we are at the fourth suffix, which is ABA $. So we start at the root node. We look for an A, which we do have, so we travel down it. We look at the next character, which is a B, which we look for an outgoing node B, and we have that, so we travel down it. And then we look for an outgoing node A, which we do have, so we travel down it. And then we don't have an outgoing node for a $, so we create it. And then we do the same thing for BA $. So we start from the root, go down B, go down A, don't have another $ outgoing edge, so we create it. And then we do the same with a $ and $. Yeah, if you just click again. Yeah. So this is your complete try. And if you click again, you'll notice that each path from the root to the leaf, to any leaf, represents a suffix. So root to the $ node is a suffix, and then root to A B B A $, that's a suffix. And this is also conversely if each suffix is represented by a path from the root to the leaf. So it works both ways. If you have the path, it's a suffix. If you have a suffix, it's going to have a path from the root to a leaf. Okay, so that's how you create it. And now, yeah, so now if we go to the next slide, we'll go through some questions that might come up, and using a trie data structure is useful to answer these questions. So one really common one is to check if a text T or a string T contains a substring S. And that's the first one we'll be doing, and it's really common. And it's the first question I was ever asked on an interview for an internship. And I, did not know what tries were. But this one the tries are extremely efficient for this. Another thing we can do is check if a substring S is a suffix of a string. We can count the number of times that the substring S occurs in a string T, and we can find the longest repeated substring S of string T. We're going to go through all of these. We're going to go through the first one, third one, and fourth one, and the second one we have the slides for, but we're actually going to skip over it because it's really similar to the first one, and you can just look at it in your own time. Okay, so next slide, please. Okay, so this is the basic algorithm for finding out if there is a substring in the text. So you start at the root and follow edges labeled with the characters of the substring. If you fall off the trie, so that there's no outgoing edge for the next character of the substring, then it's not in the text or in the trie. If we finish all of the characters of the substring and we don't fall off the tree, then it exists in the text in the trie. Okay, so if we go to the next slide. Okay, so here our substring is BAA, and our text is ABAA, ABAABA, and we have it on the side there, right? Okay, so you start at the node, at the root, and you look for the first character of the substring, which is a B, so you travel down it and go to the B node. Then you look for the next character, which is an A. You look for outgoing edges for A, you find one, you travel down it, and now you're at the node for A. You look at the next character of the substring, which is another A, so you look for an outgoing edge for A. You find one, you travel down it. Okay, now you notice that you are at the end of the substring, there are no more characters, and you haven't fallen off the tree, the trie. So this means that BAA does exist as a substring of the text. Okay, next slide. And this is another longer example. You do the same thing. You look for the first character, A. You start at the root. You look for the first character, which is A. You go down it. You look for the next character, which is B. Search for outgoing B edge. You find it. You go down it. Next character is A. You look for outgoing A edge. You find it. You go down it. Next character is A. You look for outgoing edge A. You find it. You go down it. Next character is B, you look for outgoing edge B, you find it, you go down it. Next character is A, you look for outgoing edge A, you find it, you go down it. You look for next character, there is no next character, and you realize you haven't fallen off the tree, so yes, it's a substring. The next slide, please. And this is an example of when it's not a substring. So you start at the root node, you look for next character, which is B. You look for outgoing edge B, you go down it. Next character is A. You look for outgoing edge A, you find it, you go down it. You look for next character, which is A. You look for outgoing edge A, you go down it. You find it, you go down it. Next character is B. You look for outgoing edge B. You find it, you go down it. Next character is B. You look for outgoing edge B. It doesn't exist, so you fall off. And then it's not a substring. Okay, so next slide. Okay, and these are the slides for checking if it's a suffix, and it's exactly the same thing, except that you also look for the $sign at the end. So we're going to skip through this one and the next slide. So, yeah. And then, yeah, so we'll just go to that. Yeah. Okay, now this is also a really good question, and it comes up a lot. The number of times the substring occurs in the text. And this is the algorithm for it. You travel down the path corresponding to the characters in the substring that you want. If you fall off, as we saw before, then it doesn't exist. So obviously the answer is 0. So you return 0. If you end up at node n, and n is the number of is the last node of the substring characters, you go to that node, and then you look at its children branches, and you find how many of them have a leaf node at the end. And the number of leaf nodes that come out from the tree that starts from node n is the number of times that that substring occurs in the text. And if we go to the example, it's a lot easier to understand. So if we go to next slide, please. Okay, so there on the left, you have the substring that we're looking for, which is ABA. And you look at the text, and it's ABAABA. And if you look at the occurrences, they happen once at the start and once at the end. And so the way to figure this out is you start at the root node. You look for the character A. You check next character in the substring, which is A. You look for outgoing edge A. You find it. You go down it. Look at next character, and it's B. So you look for outgoing character edge B. You go down it. You find it. You go down it. And then A. You find it. You go down it. And now you're at the end of your substring. So now you look at So now you see the node n there. That's the root of this baby tree, right? That's the root of the subtree over there. And so you look at how many leaves that it has. And you can do that using a depth-first search. So if you click, you see that there are 2 leaf nodes. So you know that there are 2 occurrences of the substring ABA within the text ABA. Okay, next slide, please. Okay. Another really common question, which is longest repeated substring. And the algorithm to find this is find the deepest node with more than one child. And if we go to the next slide, yeah. You can basically do BFS or DFS, well, DFS actually, to find the deepest node with with most children. Wait, can you go back one slide? Sorry. With more than one child. Okay. Yeah. Yeah. So you're looking. Oh, sorry. Go forward 2. And again. Yeah. Okay. So you're just looking for the deepest node with more than one child. So you have 4 contenders. So if you start at the edge obviously has more than one child, right? So, maybe that's the that's a contender because it has more than one child. But it doesn't have any characters in it, so it doesn't count. So if you look, there are 3 nodes that have more than one children, and one of them is if you start on the rightmost branch, which is just a $sign, you go to the next one, which is the B branch. You go 2 levels down, and that node has 2 children. So that may be a contender, and it's 2 levels deep. Okay, and then you go to the A branch, and the first node at level 1, that node has 3 children. So that's potentially a contender. But the last contender that we looked at is 2 levels deep. So this one can't be the correct one because it's only one level deep with multiple children. So you go down, and if you go down the ABA path there, you get to a branch that has more than one child, and it's actually deeper than the last contender that we had that was 2 levels down, and this is a depth of 3. And if we look at the rest of the tree, we don't have any other nodes that are deeper than 3 nodes down with multiple children. So this ABA is the longest repeating substring within this string. Okay. All right. And then if we go to the next slide, we have a Python example of how to implement the trie. And the first function over there just creates the trie in a similar manner to how I was explaining, where you start at the root node, you see if you have any of the characters, you don't have them, and then you just go in and create them. And you do this for all of the suffixes. And then you have a follow path function over there. You have a has substring function over there and has suffix function over there. So has suffix obviously answers the second question. Has substring answers the first question. And then follow path is what you will use to go and traverse the paths. And you call them in has substring and has suffix. And I'm not really going to go into this too much, honestly, because I haven't implemented this myself. So I can't go over it with you guys, but there's a link over there where you can see the actual code, and I would highly recommend that you go and implement this yourself. And we're going to try and have this implemented for the meetup tomorrow, and it'll be fun to see it work. Yeah. Okay. So if we go to the next slide.
1 second, sorry.
Yeah. Here's the repeat of that YouTube link, and that's where I got all this stuff from. And it has the code for it, the implementation code. It has links in it. And I really, really recommend that you go and watch it. It's really good. It's much more thorough than what I did here because I kind of hurried through it. And it expands into compact tries, so suffix trees and prefix trees. And really good. Oh, and the other source I used was Wikipedia for the pictures. Yeah. So, okay, that's it for me on the tries. So, Jaren, you go.
All right, moving into graphs. So, next slide, please. What is a graph? A graph is just basically any set of objects and the connections or links between them. So, in the slide that you'll see here, you'll see just sort of a simple graph with 6 nodes. These objects can be called nodes, vertices, or points, depending on sort of the implementation. And then the links and relationships between those points are often called either edges, arcs, or lines. For the purposes of this presentation, I'll try to consistently use the words nodes and edges so that we're all on the same page. Next slide. So usually a graph models something from the real world. A couple of the real world applications that you might see graph used for are, one is sociology, so social network theory. For example, mapping out the graph of someone's Facebook relationships where each node is a person and then the links between them are friend requests or friend links. So you can kind of map out one's immediate social network and then all of the people that they can be reached from via friend relationships outward. Similarly, in linguistics, and the example graphic you'll see is from semantic reasoning, but within words and sentences, there are lots of links between words, either words that have the same meaning or breaking down the structure of a sentence into kind of nouns and verbs. A lot of natural language processing algorithms might represent language or semantics as a graph, and there's actually graph databases and ontologies that do this really well. And then lastly, a physical model of elements in biology might be represented with a graph where each molecular structure, the nodes within that are the elements, and then the relationships and the bonds between the elements might be represented with edges. Next slide, please. On the terms we might use consistently throughout this presentation, A node set is just a list of all of the nodes in your graph. So they might be named, they might be numbers, but just some sort of identifier that represents each node in your set. So for the given graph here on the right, the node set includes the numbers 1 through 6, the integers 1 through 6. And like I said, each graph normally represents something in the real world, so this set comes from the infinite set of integers. An edge set is a list of pairs or tuples of connected elements. So each edge has two nodes that are associated with it. And so the node sets here, if you look, I don't have access to the cursor, but it's okay. There are 6 nodes, and there are 7 edges between those nodes, and each of those edges is represented in this edge set. So you can see a connection between the nodes and 4 and 2. Between 3 is no edge number 1. So 6, 1 is not in our edge set. And adjacency, two nodes are adjacent if
Hey, Jaren.
If there's a pair in the node set with that.
Hey, Jaren, you keep breaking up a little bit.
Okay, sorry. Hopefully you guys can still hear me.
A little. You keep like fading in and out. Can you say something?
Hopefully it's not my. Yeah, hopefully it's not my internet connection. Can you guys hear me?
Yeah, this is good. I can hear you now. Yep.
Okay. I'll try to talk slower, but let me know if I fade in and out again.
Yep, I will.
Okay.
Slide.
All right. So next slide. Yes, please. Different types of graphs. So in the example that we saw in the previous slides, there were just lines between each of the nodes, which means that it doesn't really matter. There's a relationship between those two nodes, but it doesn't really matter which direction we're moving. But in a directed graph, the order of the nodes in the edge set matters. So on the left, we'll see a directed graph with the nodes A, B, C, D, and E from the finite set of letters in the alphabet. And so there are 5 nodes in this set. And then the edge set, we'll see an edge from A to B. And since we see in the example, there is an arrow that is going from A to B, so that order does matter. We'll see it even more explicitly with the connection between A and C. A and C is different from the relationship from C to A. And we can see in our graphic that there are 2 lines, and that could also be represented just with like a single line with 2 arrows, like an arrow on either side. So, it's just sort of convention. But that, the A to C direction and the C to A direction are both distinct edges in this edge set. And then there's also one from C to D, from D back to A, and then one from E to D. In directed graphs, one important kind of term, 2 terms that kind of go together are called sources and sinks. A source is a node that only has outgoing edges, so no directed nodes coming into that node. So in our directed example, one source would be the node E, where there's one connection between E and D, and there are no other connections coming into that node E. It's only going out. Conversely, B, the node B, is a sink because there is only one connection between it and any other node between A and B, and A is coming into B. There's no outgoing nodes from B to anything else. And then we see on the right there's an undirected node that's similar to the directed one, where sort of the order between A and C doesn't matter. We see the difference between the one on the left and the one on the right. Next slide, please. Okay, cyclic versus acyclic graphs. So a cycle in a graph is a path along the directed edges from one node back to itself. So if your directed graph has one or more cycles, then it is a cyclic graph. If it does not, if there are no cycles in your graph, it is acyclic. So again, in the example on the left, we can see that this graph is cyclic because there are 3 nodes from which you can make a cycle from itself back to itself. So let's start at C, for example. If you start at C, there's a path from C to D, path from D up to A, and then a path from A back to C, and that is a cycle from C, D, A, and back to C. You can see the other examples from D and from A as well. And then if we take out that one relationship between the direction from A to C, this graph then becomes acyclic. There are no cycles between this graph, although between A, C, and D, it looks like a cycle, right? Because there are connections between all three of those nodes. The direction matters here. So there is no way for you to go from one direction to the next and get back to itself the way the arrows and the directions are implemented in this graph. Okay, next slide. And then the last type we'll see is weighted versus unweighted graphs. In all the examples we've seen thus far, they're just plain nodes that the nodes themselves are usually where the information is kept, right? And then the edges are just lightweight bonds or connections or relationships between those things. Well, in a weighted graph, each edge itself also carries some information, and it has a cost associated with it. That cost might be actual monetary cost, as in this example, where I just made, a completely made up example, but of sample cost, like physical cost, of flights between various cities in the United States, mostly in the East Coast. So, a flight from Washington to Philly might be $75. A flight from New York to Miami might be $220. And there is a monetary cost to these flights. If I was trying to figure out a route from Washington to Miami, which in this graph there isn't a direct one, I could say, oh, I could go from Washington to New York to Miami, Washington to Philly to Miami, Washington to Philly to Chicago to Miami. But each of those things has a penalty associated with it, right? The one modeled here is cost, but there's also another one, time. It's not every path in this graph is created equal. One other, time and money are sort of really easy to visualize, but I've also seen weighted graphs used for distance. So if you're trying to map out the length of wire, for example, and you want to kind of hook up one server to the next in this huge server farm, you can say, look, let's make a graph to find the shortest path where I have the least amount of wire to connect all of these things together. So that's one example. All right, next slide. We're going to start getting into traversal here. So traversal, if for those of you who were on our session last week or 2 weeks ago, we did tree traversal. And trees are sort of a special case of graphs where they're always acyclic. You cannot go from a leaf of a tree back up to its parent or vice versa. There's always sort of one direction in a tree. Whereas one direction in a tree, which is sort of a special case of graph. The traversal is just visiting or processing every node in that graph via some algorithm. With trees, the structure ensures that we are kind of only going to ever visit each node once. The way trees are set up, you go from the root to all the leaves are sort of one direction and one logical structure there. You never really go back up to the parent to reprocess. Whereas with graphs, we've seen in some of these examples, there can be cycles, there can be paths from one node back to itself, and our algorithms need to take that into account so that we don't end up with unnecessary redundancy, right? We're processing the same nodes over and over again, or that we're in infinite loops in our graph where we're in a state where we can't get out of this processing cycle, and try to have the maximum performance. Next slide. So the first traversal algorithm that we'll go over is depth first search. And for those of you who were here last week, I think all the algorithms that we went over for tree traversal were all depth first. The difference was sort of where the node was processed, whether a node was processed before its children or after its children, or kind of where the processing of a node fell within the processing of its children. But they were all, you kind of went down as deep in the path as you could go before kind of processing. Here we're going to do the same thing with graphs. So the algorithm is to explore the furthest or deepest nodes first before you backtrack and kind of go to the next path in the graph. So we're going to go through this. Hopefully the recursion, I've tried to illustrate it so that it'll be a little bit clearer, but if there's any questions, I've got Slack open. We've got the Google chat open, so if there's any questions or you need me to slow down, please let me know. All right, getting into it. Next slide. So given the graph that we have here, I'm going to start at node A. And we can, I want to highlight too that I've got a data structure somewhat of our graph in this, it's labeled with G. So G is a graph where it has a set of nodes A through E, and for every node, noted with the letter and then the arrow, every node has a state for whether it's been visited, which is true or false, and then the set of adjacent nodes to that node. So for example, I'll just go over one. If you look at the line for C, it has not been visited, so visited equals false, and the adjacent nodes, which are the nodes that can be reached starting at C, are A and D. So that's in that array to the in the C line for adjacent. Okay, so if we're starting at A, we first label A as visited, so you can see here visited equals true in green, and then we process A. The processing of each of the nodes will just be printing it to our output. So you can see over sort of on the right under the graph, output equals A, and that's also in green. Then we go into our for loop and into recursion. So it says for all of the adjacent nodes, basically, if that node is not labeled as being visited, then recursively call depth first search with the same graph and that new node. So the first adjacent node to A, and it's denoted with this arrow, is B. B, if we look on that line, visited equals false. So we're going to recurse into depth the same algorithm, depth first search, with the current graph and then that node B. Next slide. So we can see that A went from, do I have it up? Yeah, A went from green to blue. We said, okay, we visited that. We're now on to B. So we label B as visited. B is now visited equals true in green. And we add that to our output. We process B by adding it to our output. Then for all the adjacent nodes to B, if it's not labeled as visited, then we recursively call depth first search again. So what are the adjacent nodes to B? We see from this arrow, it's showing that E is the next adjacent node to B. So then we see that E also has not been visited. So we go into depth first search again with E as the current node. Next slide. So then we now label E as visited and process it, add it to our output. We can see that's in green. E is now the current node, and we add visited equals true to E. For all the adjacent nodes to E, which is just D in this case, if it's not labeled as visited, which it's not, recursively call depth first search again. Next slide. So okay, here we go. So we add label D as visited equals true to D, and then we add that to our output. For all the adjacent nodes to D, if it's not labeled as visited already, then we recurse into it. But we see that the only adjacent node to D is A. And if we look on the A line, A has already been visited. So we do not recurse into depth first search again. We start kind of backtracking. So if we look at the path we've already chosen, we've gone from A kind of as deep as we can go. We've gone as far as we can go along the current path before backtracking. Next slide. So we backtrack and we're back here on E. E doesn't have any more adjacent edges. D was its only one. So we keep backtracking. Next slide. We keep backtracking again. Does B have any adjacent nodes? It doesn't. We backtrack one more time. Next slide. So we're back at A. We already processed B, and we kept processing all of B's adjacent nodes until we kind of got back to where we are. So, but this is a for loop, so we have to continue processing the rest of A's adjacent nodes. So, if it's not labeled as adjacent, C is the next node. It's not labeled as visited already. It's actually the only one left that hasn't been visited. So we're going to call depth first search with C now as the current node. Next slide. So we can see we add C to the output finally. We mark it as visited, and we can't really recurse anymore, right? C doesn't have any adjacent nodes that have not already been visited. The only adjacent nodes to C are A and D. Both have been visited. It's all of our nodes have been visited, and we kind of recurse back, and we're finished here. So our output, we can see at the bottom of the graph, is A, B, E, B, C. We went as far as we could down the B path of A, and then we finally went back to its next adjacent neighbor, which was C, and that's it. So are there any questions here? I'm going to slow down for just 1 second. I don't see if there's any questions.
There's none that I see on the YouTube link or Meetup.
Okay. Okay, cool. So next, we're going to go into breadth first search. So the difference between depth first and breadth first is that with DFS, you go as far as you can down one path before you turn around. And we saw that with, there's a cycle between in A where we could go all the way down from A, B, E, and D before having to kind of backtrack and having nowhere else to go. With breadth first, you visit all of your neighbors first, and then you start visiting all of their neighbors, and then you visit all of their neighbors. So breadth first search is good for kind of finding shortest paths because you explore your inner network before you go to the next biggest network and to the next biggest network. We did DFS with recursion, but this one we're going to do iterative. Hopefully, I again tried to make everything color-coded and step through so we can kind of see where we are. But if there's any questions, please let me know. All right, next slide. So since this is not a tree and there isn't like a root node, we kind of arbitrarily pick a node to start from. So the node that I chose to start from was A. And the structure that we're using here, we still see over on the right, the same graph structure that we used in the DFS example, but I added 2 data structures here so we can visualize. Usually breadth first search is implemented with a queue, Q-U-E-U-E, the data structure where things are added to the stack. It's first in, first out. So the things that are added first get removed first. First in, first out. And that tells us sort of where we are in the stack. It's a little bit easier to visualize than recursion because you can actually see what has been added to the queue, and then the second data structure popped. That'll be what has been removed from the queue, just so we can kind of keep track of where we are. So if we're going down this procedure, it says queue.enqueue, and that just means add something to this queue. So it says add the vertex, our current vertex, to the queue. So we see here that I've added A to our queue, and then we label it as visited. So visited equals true for A, but nothing yet has been added to our output. We're just sort of checking off the box that we've visited this node. Then while the queue is not empty, we pop off the first thing on the queue, and actually you can go to the next slide. So we see that A now has been popped off the queue and put into the popped list. So there's nothing left in our queue. That's the point when we start processing A. So we see here A has been added to the popped queue, and it's also been added to our output because we processed it. Next slide. So then we jump into this for loop. For all of the adjacent nodes to A, which are B and C, and we've got them color-coded here. So B and C. For all of the adjacent nodes to A, if it has not been labeled as already visited, add it to the queue. So that's queue.enqueue, add all those nodes to the queue. Then we add B and C, and then label them both as visited. And we can see in our data structure on the right, both B and C have now been added as visited equals true. So but we have not, you see in our output, we've not added them to the output. We're just sort of putting them in the line to be processed. We have not actually processed them yet. Next slide. So then we are still in this for loop while the queue is not empty. So the queue is not empty. It had B and C in it. So we go to dequeue, which is pop something off the queue. So B is the current node that we popped off the queue, and you can see C still left in the queue to be processed, and B has been popped off now. It's at the end after A. That also means that B has been processed now. We add B to our output. So our output is A and B. Next slide. So then we jump into this for loop. For all of the adjacent nodes to B, if it has not been labeled as visited already, add it to the queue and queue it. So we see in this step we added E to our queue. The only adjacent node to B is E. So we've added that to our queue. Again, this doesn't process them yet. It just says, look, that's the next one in line to be processed. Okay? Then We jump back up to our for loop, and our queue is still not empty. We pop C off the queue because that was the next one in line. We're adding things to the end and popping them off the front. So C is our current node. Pop that off, and we processed it. Added that to our output. So our output is now A, B, C. Next slide. We jump into the for loop. Next slide. Am I on the same slide?
I think this is the last slide that I have.
Uh-oh. Because I've got...
Do you have more?
Yeah. I don't know if because you started... I was modifying them sort of at the last minute, so I wonder if
okay,
because
let
you
me
started
go
it...
back.
Okay.
Give me a second. Let me refresh. Yep, there's more. You're right.
You should have... Yeah, it's 52 slides.
Okay. I think I can get them up.
Okay.
Yep. Okay,
There
cool.
we go. Okay, so we were on slide 48. Is that where you are?
I am where C was just popped and processed.
Okay, let me go back.
47.
There.
Okay, there.
Okay, yeah, 47. Okay, so 48, go to the next slide. And so C was just processed. And for all of the edges, so all the adjacent nodes to C that have not already been labeled as visited, then we add those to the queue. So if we look at our data structure, C has 2 adjacent nodes, A and D. Those are the only 2 nodes that can be reached from C. A has already been processed. We have visited equals true in A. So we add D, the only remaining adjacent node for C, to the end of our queue. Okay, so next slide, please. We go back up to our loop to start processing the next node, I'm sorry. The next node in the queue was E. Now, at this point, you can see that all of our nodes have been visited, which means they've all been put in line. They've all been put in the place where they need to be processed, but we see that we only have A, B, C, and now E in our output. So that means that everything is already in the queue, and then all we have to do now is just sort of pop them off in the right order. So we've processed E, we've added that to our output. Next slide. And so for all edges that are adjacent to E that have not been visited, there aren't any. So we kind of come out of here. The only last thing in our queue then was D. That gets popped off and added to the output, and that's it. The queue is now empty. There's nothing left to process, and our output is A, B, C, E, and D. So we go to our last slide of just the comparison of the two. We can see from depth first search that our output was A, B, E, D, and C. So if you follow that path, starting with A, we went as far as we could down this path before backtracking. And C was sort of the last, even though it was a direct adjacent node to A, since it was the furthest away in that processing line, it didn't get processed until the end. Whereas with breadth first search, you process all the neighbors first. So if you start at A, the only 2 neighbors, the only 2 nodes you can reach are B and C. Then all of B's neighbors get processed. So that's where E comes in. And then C's neighbors get processed, and that's where D comes in. So you see A, B, C, E, D. All right. And then this is sort of the end, but 2 common problems. I didn't want to go too far down the line because, yeah, we're almost at time now. But if you want to do some further reading into common problems that are asked using graphs, especially in interviews, the traveling salesman problem, which is essentially finding the shortest path between 2 nodes and visiting all of the nodes in a graph exactly once. So that's a traveling salesman problem. And it's called that because the scenario is that you're a salesman, you're new to this town, and you have to visit all the houses in the town, but you don't want to kind of backtrack. You know, you're a salesman on the go, you don't want to waste any more time than you need to, so you need to find a way to visit every house in that neighborhood exactly one time. Dijkstra's algorithm is the shortest path. It's one of many interview question. So that's all I have, but there's definitely more resources out there for looking at graphs.
Darren, could you repeat what you said about Dijkstra? You like cut out completely when you were talking about it.
Oh, sorry. Can you hear me now?
Yeah.
Yeah.
Sorry, my internet is a little bootleg. But Dijkstra's algorithm is finding the shortest path between two nodes. And there's lots of modifications of it and variants of it with different names, but because sometimes Dijkstra's takes into account like simple graphs, but there are other algorithms that you might use if your graph is weighted or if there are special cases of graphs that so there's Dijkstra's is sort of one of the more simple algorithms, but there's definitely two variations of it.
Cool. Yeah, and I just wanted to add that I rushed through a lot of the stuff for tries because I wanted to, like, get it done quickly. So if you have any questions, post them up or ask them. And, we have the meetup tomorrow, so let's talk about it tomorrow as well if you have any questions. Yep.
Awesome. Thank you both. This was excellent. Yeah, so I guess we'll see everyone who is watching and listening in on Slack tomorrow.
Yep. Perfect. Yeah, thanks, Amy, for going through the slides.
Oh, not a problem. Thank you both. All right, I'm going to stop broadcasting now, and I'm going to edit the video and then put it up on Slack and Meetup so everyone can watch it who can join us.
Perfect.
And
Okay.
Amy, can you put a link to the slides too, just in case?
Yes.
I don't know if, because of the whole not refreshing, so that people at least have the most updated versions of the slide, even if the syncing was a little off.
Yes, I can definitely do that. I'll put up both.
Great. Thanks.
Okay, thanks.
Bye. Happy Sunday.
All right, have a good day, everybody.
See ya.
Bye.